fifth and final lecture on primordial cosmology by Gonzalo. So Gonzalo.
Yeah, thanks, Rogerio. Okay, so the plan for today is quite ambitious. I want to cover two topics. So I told you yesterday that yesterday's lecture was meant to be the most important one in the sense that the outcome of yesterday's lecture was the observable that we can constrain with current observations coming out from inflation, namely the power spectrum. Well, today will be almost equally important in the sense that I want to discuss the prediction of two additional observables on top of the power spectrum, which is the power spectrum of tensor modes and the primordial bispectrum, yeah, which parameterizes primordial non-Gaussianity. Those observables have not been observed, yeah? And that's why they're so important, because these predictions basically enlight people constructing observatories and guide them towards what should they do in order to further constrain inflation. So these are important quantities that we hope to observe in our lifetime. Yeah. This one, okay, might be around the corner. Yeah, tensor modes. This one looks pretty hard, and maybe it still requires decades and decades of hard work. Yeah, not from the side of theorists, but from the side of those of you doing observations. Good. So as a starting point, I want to go back to the Einstein-Hilbert action. So I will start with tensor modes, yeah, which is easier actually. And remember that when we wrote the well, everything is there. This is in co-moving gauge. So remember that the only thing I need to specify here, we have the lapse. The shift is hidden somewhere here. Remember, please. I need you to recall all those facts. And of course, we have the spatial matrix, which we are calling it Qij. And in the previous yesterday's lecture, we wrote this, okay, to study the dynamics of curvature perturbation. Yeah, but now I want to study the dynamics of tensor modes. So R is not the main star of today's lecture, at least not at the beginning. I will come back to R later when we study primordial non-Gaussianity. So, okay, now our metric is reduced to that, no scalar fluctuation, but I want the tensor mode back. Remember that at some point on Wednesday, I deleted the tensor mode. I said, well, we're not interested in this tensor mode for now, but now I want to go back to it. Yeah. So maybe you recall that the tensor mode appeared among the other perturbations. There were many perturbations. There were 10 of them, and 2 of those are described by the tensor modes. So I want to put them back, and they were written. They appeared like this. Yeah, that's how the tensor mode appeared in that discussion. But I want to do something. You might recall again. Let me go back another second. That when we discuss curvature perturbations, we actually did the following. We had this plus 2R, or 2B at the beginning, but in co-moving gauge, this ended up being 2R. Yeah, remember that? And then I promoted this. I said, well, we'll stop working with that version, and I will work with my version, which will look like this. Yeah, remember that? We did that yesterday when we derived the action for the scalar mode. Yeah, for the curvature perturbation. That's what we did yesterday. And as a matter of fact, it's very useful to do more or less the same here. This might look a bit uncomfortable for at the beginning, but it actually has a lot of advantages to do precisely this trick, but to do it up there. So one can do the following. One can just promote this to be the exponential of gamma ij. Yeah? I would put the indices down here. And in fact, many computations come out so much simpler if you do this. Yeah? When you compute, for example, the determinant of qij, whatever, there are a lot of computations that get much simpler. So to give you a sense, but what do I mean by the exponential of gamma, which is a tensor, yeah, ij? Yes, this just literally means that we have to interpret this as an expansion of matrices. So this will be just this term that will be the first term, but then comes there are quadratic terms. Yeah, so this will be, for example, 1/2 of gamma I k, gamma k, j, and so on and so forth. Okay, so it literally means that. Correct? Repeated indices will mean a sum. Okay, so this is what we have. Yeah. Okay, that's one thing. Details you can find in the notes for sure. Yeah. Okay, and so remember, no scalar perturbations, just the tensor mode. So we need to figure out what's the form of the action. And I don't need to take care of the scalar part of the inflaton. Yeah? I can forget about that. This is where the tensor mode lives. The tensor mode is coupled to the scalar, but those couplings are of a higher order. And here I want to study the linear dynamics of tensor modes. So I only need the quadratic action for the tensor modes. And so this is the only source of the quadratic action for the tensor modes. Yeah? I don't need to look elsewhere. Okay, so this is the only part that I need to, is the only relevant action for this problem. Great. So having said that, let's, I will do the work for you. For example, I will just make statements about the objects that appear here when you work with this definition of the tensor mode. Yeah. For example, well, n is just 1, right? It's 1 because there are no perturbations, no scalar perturbations, so it goes back to just being 1. Remember that n was perturbed, so it was 1 plus delta n, but there is no scalar perturbation in this problem. Delta n is equal to 0. Yeah? That's the first thing. Another thing is that you can show that the determinant, the square root of the determinant of q is just a cube, and the tensor mode disappears altogether. Yeah, is just doesn't appear. The other thing is that you can go and compute the Ricci 3. Yeah, and it's a lengthy computation for sure, but it's a very simple expression that you will finally get. You will obtain the following. Remember, repeated indices mean sum, so you will get to this. Okay. Other simplifications is that, for example, k squared. This is less obvious. Remember, this is the trace of the extrinsic curvature squared, and this is found to be just like that. No evidence of the tensor mode whatsoever. This is also thanks to this definition, so it makes life simpler. Computations are really not so complicated. And then, finally, another piece of information is that this becomes that's the result. And that's it. There's no more elements into this problem. So after that, after we grab all of these expressions, we put it back into the Einstein-Hilbert action, the action for the tensor mode becomes just that. Amazingly simple. Tensor modes are way simpler than primordial covariant perturbations, as a matter of fact. Yeah? I can assure you. And you can see a difference between, it's worth noticing this difference. Do you remember the action for the covariant perturbation? Let me actually remind it to you. It looked like this. Well, I'll write it in a similar fashion, just for you to compare. That was the action for the curvature derivation. So you can compare. And there is a feature that is quite evident, a difference between both. This one is essentially the same as here, except for the sum of indices, but forget about that. So if we compare the rest, we see that the main difference is the appearance of epsilon. Yeah. So that, in part, this makes life more difficult for dealing with R. Yeah. And here is we don't have that part. Okay. And this will matter actually soon when we compare the power spectrums of the power spectrum from both sides. The other things are factors which are relevant actually. This 1/8 and this doesn't have anything, and this will come back later. Okay. So bear in mind those aspects. Great. Any questions? I should remind you, by the way, I didn't say this, but you know this, that tensor modes are constrained to satisfy, to have zero divergence, right? And zero trace. Don't forget that. So these two things are very important. Okay? And because of that, dealing with this action is not really trivial because you see, where is that information? Where do we see these two constraints in this action? Well, nowhere, right? So you need to know these, that those constraints hold for this action. Otherwise, if you don't, then you vary this action and you will get back equations without this information whatsoever. Yeah? So you must be careful there. Yeah? I think Jose probably was way more careful in that sense, that you made efforts to have that evident elsewhere, everywhere in the actions. Here, you need to know in advance, otherwise we lost track of that piece of information. Okay? So be careful with this this expression because there appear to be way more information than there actually is. You need to remember that these two things hold, yeah, and they're not there to be seen. Yeah. So what I will do, I don't know if this is the best way to proceed, but it works. I think I can delete this. Is trade this symbol gamma ij, trade it by the propositions themselves. Yeah, make them explicit, because you know that these two conditions reduce the initially 6 possible degrees of freedoms down to 2, right? 6 because this is a 3×3 symmetric matrix that has 6 degrees of freedoms, but with these two conditions you get down to 2. Yeah, and so I will do something that I think you already discussed with Jose to some extent, which is to write the tensor mode explicitly. I will do it in first space as the sum of 2 contributions with polarization matrices that will just like that. Did you, Jose, well, did you, Jose, introduce these quantities, or you work them with a different notation, perhaps? Or? Okay. Okay, but we're talking about the same thing, nevertheless. and then we can write this. Okay, so I'm happy that you saw already these matrices with Jose. I don't know if it's exactly the same notation. Perhaps not.
I didn't do it.
Oh, you never. Okay. Never mind. Yes. Okay, great. I was hoping that I didn't have to do it, so I will do it now. Okay, so we expand in this basis. This is just a basis, yeah? So you know there are 2 degrees of freedom. So these degrees of freedoms are here. They satisfy equations of motions, right? So they propagate, yeah? And these matrices are just a basis that reminds us of these constraints, yeah? So they keep track of those constraints, yeah? So that means that these matrices, by the way, they only depend on the direction. Yeah, you will see why in a moment. It's because these things really affect only that information. These constraints do not care about how large is the wave number. Yeah, how big it is. Those constraints do not relate to that aspect of the problem. So you can see that this expression. This expression implies, so the traceless and divergence-less conditions, yeah, imply the following 2 conditions on these matrices. So this A labels these 2 symbols, plus and cross, like this. Which, okay. Okay. I don't. Yeah, please. I don't know what's the problem.
Like this.
Okay. So it was not a fashion issue. It's a technical issue. Okay. Okay, so A labels the 2 modes, yeah? And so this is the first condition. You see, has nothing to do with the size of K, it's just the direction, yeah? And then we have the traceless condition, which is that just, just put a trace like that for the two modes, yeah? So now you can choose these matrices. You just need, there are only 2 of those that satisfy this condition. There are no more. Yeah, you can do the counting. Yeah, there are only 2 matrices in 3 dimensions that satisfy this, and now it's up to you to choose them. Yeah, there are bases, so you can choose the bases. It's like choosing the direction of x and y in a Cartesian plane. So now it's up to you. Yeah, so we can choose them, and the way we will do it. This is not the only choice. Yeah, but it's a common choice that you might find. Is that the multiplication of this sum is given by acquires this form. Yeah, we can choose the basis to satisfy that, and observe this is familiar, I hope. It's just a projection matrix. Yeah, it projects any vector along the plane orthogonal to the wave number, the wave vector. Yeah, and then there is another condition that we can impose, a normalization condition, which is this one. So if we take the trace of those 2 matrices together, we choose them to satisfy that. Yeah, these are just choices. You can choose other bases, but these are good choices. By the way, I found some, if you're comparing with the notes, all the questions have been written. They don't always look exactly the same because I've been noticing some typos or some conventions that I'm modifying, but I will update the notes as soon as possible. Okay, and just an example. This is such a typical example that, which is to at least show how this looks for example, a given direction. So we choose how this matrix looks, for example, in the z direction. Let's say the vertical direction. It's just to have a hold on this expression. So you might find very typical expressions. This could be E plus and then E cross. So these are just examples. It's up to you. Yeah, these are not unique, but it's most of the time is what I mean. Almost always is what it is meant by those two possibilities. Then you can obtain the matrices for any other directions by just rotating these matrices in a specific ways into other directions. Yeah, but we don't need to know them. It's not really relevant. Now here comes the important point. After we impose this, yeah. Now remember we have these two modes. We have this algebra here. Yeah, these are conditions respected by the matrices. So now we can plug those expressions at the left-hand side of the blackboard. We plug them here. We play with the algebra of the matrices, and things start to simplify. We have to. No, it's really super simple. So I will just tell you what happened. I can erase these symbols here, and I will. So this becomes a sum over the two modes, yeah? And this is just end up looking like this. That's it. This is in coordinate space. So this here, what I'm saying there, let me just give one step back, is that gamma A of x and t is just the Fourier transform of gamma A of k and t of e to the plus ai k dot x. So there's been sort of going forward and backward into Fourier space, yeah? But we finally get to this point, yeah? And so this is the action describing the propagation of the two modes. And now we see explicitly, yes, there are two modes propagating. Before, we might have thought that there were more, 6 modes, but there are really 2. Yeah, so now we're not concerned anymore with the constraints. They're left behind. Okay, and we get to this point. Any questions? And now, if you follow with attention last lecture, I hope you learn how to deal with this to quantize it. It should be way easier for you to quantize this expression. Just because epsilon is not there, but the steps are exactly the same. So remember, what did we do to quantize this? We first moved to conformal time. Yeah, that was the first step. Let's do it here. Yeah, so when we move to conformal time, let me remind you that conformal time was defined as this. Yeah, that's the defining property for conformal time. So we can just replace dt by conformal time. So let me do the replacement here. So we have conformal time, and now this increases to 4. There you have. Here's the same. Well, we did it already for the curvature. There it is. Yeah. But this also requires dealing with derivatives. These are in cosmic time. So if I replace derivation against cosmic time, it comes out that over a squared. Yeah, and now we cancel this, and this goes to 2. Yeah. So this simplifies things a little bit. Okay, now we have that action. Yeah, we did the same here for the co-moving mode. So I will forget about the co-moving mode here. So I'll just erase it, not to be working more than it should. Yeah. What was the next step? Can anybody here remind me what is the next step from here? Or what should be the next step? What do you think? Try to remember what we did here when we quantized R. So what should we do now with this action? With? Okay, great. We will do that. But this action is still a bit uncomfortable. Yeah. I'll tell you why. Because if I work out what is the canonical momenta, let's say I want the canonical momenta, for example, for that guy, yeah, for the mode cross, yeah, then what will come out from here? And you will see that it will come out a squared over 4, yeah, gamma a prime, yeah, and which exponential? All right, no, that's when we got to this point, we already reduced the action to the quadratic order. So the role of the exponential is left behind. Yeah. But we didn't learn how to quantize this. This can be quantized, by the way. There's no problem whatsoever. Yeah. Perfect. That's what I'm looking for. We need to do it's better to do a field redefinition, just because we learned to quantize with a canonical, what's called a canonical field. Yeah. So it's So let's follow the rules that we already derived, right? So why this can be done in other ways. You don't need, you're not forced to do the field redefinition, but that's the way we learn it. Yeah. So we will define a canonical field. Yeah. And this the definition, just not to get the factors wrong, will be given by this combination. Yeah, this is the field redefinition I will propose. Yeah, and the result of this is that now M Planck disappears. This will become the sum 1/2 d3x d tau, two integrals. A disappears, becomes absorbed by the field redefinition, no more. I have to perform partial integrations to move terms from one place to another. So we have this squared over there minus nabla UA squared, yeah, and then some terms pop out thanks to the field redefinition. And this look like in the following way. And I'm just repeating what I did yesterday, by the way. So U squared, thank you. So I did the same approximations. You might remember, for example, that yesterday we all agreed that yes, I will write it in this way, that t squared, no, how do, yeah, this is okay. Tau squared is 1 over a squared, h squared, 1 minus epsilon. Remember that, yeah, we derived it yesterday. Well, that is also imposed here, yeah, so all of that goes, yeah, and how to relate tau with a, so there, et cetera, yeah. So all of those steps were done here too, and we get to this form finally, and this is to first order into the slow roll parameters. I'm neglecting second order slow roll parameters, okay? So they're products of epsilon squared, epsilon eta. They are gone because we are not interested in the full thing. We're interested in the first sensitivity to the slow roll parameters, yeah? And now you see this action, and you might remember that I made a comment. This is the action for a massive field in the seater where this is the mass, right? So you can say that the mass here, let me just, yeah. So this is minus m squared over h squared. It's just a comfortable identification if you work in the Sitter spacetimes, which are super nice spacetimes. It's nice to know that this is equivalent to such a dynamics, where this mass corresponds to 3 epsilon. Yeah. And now remember that now I don't need to do anything else. Everything else is done, because what I have to do next is just repeat the same steps from now on. Yeah. The only difference, and this is the only difference, is that m squared over h squared looks different now. Yeah? Now this is just 3 epsilon. What we did yesterday is exactly the same, but it was not 3 epsilon, it was something else, right? It was, I think it was 3 epsilon plus 3 eta half. Yeah? And that's the only difference between this and what we did yesterday. Yeah? So given that I want to save time, and I don't have to do more convincing, because it's so obvious that the only difference is just deleting this eta here. Yeah, everything else goes, so we can right now, let me enumerate. We can deduce the equations of motions from this, and there you see it will appear this parameter, which in this case is 3 epsilon. There is no eta, but yesterday there was an eta. And so forth. We know how to solve that equation. Yeah. And that equation, the solution to those equations were proportional to what? Do you remember? Hankel functions. Yeah? And those Hankel functions had this new parameter. And this new parameter was what? Was, let me remind you, well, it should be more tidy. Let's go to the other side. So be very schematic here. Just to remind you what were the steps. So, okay, first step, we deduced the equation of motion, right? Well, I'll do it in, well, it's fine. So I'll do it like this. Okay, equal to 0. That is the first step. Looks the same, yeah? Exactly the same, with a mass here, with a mass parameter. And then the solution, yeah, we found that it was some factor, same factor, no difference, times Hankel functions of minus k tau, same story, so I don't need to repeat everything. And in this case, this is the difference between what we did yesterday and now. Yeah, in this case, this is 9 over 4 plus 3 epsilon. That's all. Yeah. And so on and so forth. So I will not do all the steps again, if you allow me. Yeah. Or maybe this is a great opportunity, if you have any questions about those steps, to go through them. So please, if there are questions about those steps, make it now. If not, I will then just say that repeating all the steps, I can finally write down the main result of this first part of the lecture, which is the power spectrum for tensor modes. Yeah? And the power spectrum for tensor mode, just repeating all the steps, becomes, in the long wavelength limit, of course, becomes that. That's the result. Just repeating the same steps. There is no magic in between. It's exactly the same. So I told you it was going to be easier to derive this important result. And excuse me? No, this is really 8. Yeah. Of course, observationally, you have to choose some value of k to measure. But with this expression, you learn that that comparing observations with theory, you are looking at the region when k crossed the horizon. Yeah, so that's why it appears k over h naught. Yeah. Please. 2 eps. No, well, I don't know if that's part of the is a notational question, or So, okay, let me comment on that line. So, usually when people talk about tensor modes, they parameterize it like this. I mean, you will find different letters, sometimes H. I will put T of tensor mode. And then here, K over K star, some pivot scale. And here you will find NT. Yeah, so to compare with the other case, which is curvature perturbations, where I will write it like this, K over K star of NS minus 1. Yeah? The choice of NS minus 1 is very related to what you discussed with Roman. Yeah? So this was, it's inherited from that discussion. Yeah? No, they're different. This is the power spectrum for scalar modes, where the prediction from inflation, well, now we can sort of make a table and say that inflation predicts then that NS minus 1 is equal to 2 epsilon plus eta. That's the prediction from inflation. NT from inflation is predicted to be minus 2 epsilon. Sorry, this is minus and minus. Got it wrong. Now it's correct. The prediction of NT, this parameter over there, from inflation is this. And we can also say that the amplitudes, the scalar amplitude is, well, it's h squared over 4 pi squared m Planck squared epsilon naught. I hope not to have the wrong factor. I do have the wrong factors. This is 8. Yeah. And then AT is predicted to be, from inflation, is predicted to be that over there. Yeah, okay, that's it. Yeah. So to observers, we give this table. Yeah, and so we can. People observe these parameters. This has been observed already. This one has been observed. But tensor modes, you all know, have not been observed, so we don't have a constraint on epsilon directly, and we don't have a constraint directly on h naught. Yeah. As you will learn next week, I hope, this is the first thing that you will observe if you detect tensor mode is the amplitude. Yeah. There is no hope of measuring the spectral tilt. That will have in another decade after observing tensor modes, if ever, right? So people chasing B modes in the polarization of the CMB are targeting this quantity. Yeah. Okay. Let's do that. Thank you. So, you know that, well, people doing observations are directly measuring this, but it has become accustomed to provide, to compare it with the scalar mode, right? So that's why we can define R, which is the tensor to scalar ratio, which is just delta R over delta, how I'm calling it, gamma, yeah? The opposite, right? Thank you. Okay. And you choose the scale, but this will be at CMB scales, right? So let's forget about the running, yeah? Let's just focus on the amplitudes, yeah? Because after all, people doing B modes will not observe any running. And so this becomes, well, I can just do it. It becomes 16 times epsilon, okay? And now you know why it's so hard. I mean, to go for R, because inflation predicts to be small. I mean, it's hard not because of inflation. It's hard because of it's an observational challenge. But inflation predicts it to be small, yeah? Which I guess is good because it's consistent with what's going on, yeah? Exactly, exactly. You mean this? No, these are just conventions, yeah? No. These are just, it's a matter of taste. This has big it's just, I'm writing the typical convention just for you to know immediately what it means, yeah? So this is small, and this is small, yeah? So this one means NS very close to 1, yeah? But these are just parameterizations. The important things, if you want, are here, are the predictions that the inflation provides, yeah? So that's why I quoted this as NS minus 1 and not NS equal 1, just because I want to concentrate on the right-hand side, yeah? And then there is something very important, actually, that you can see that NT is equal to minus 2 epsilon, but epsilon is equal to R over 16. So this means that NT is equal to R over 8. And this is pretty important. Why? Because it ties two observables. Yeah? This can be observed, this can be observed. So this is, in my opinion, this is the most important test on single field slow roll inflation. Yeah? Let's say you observe tensor modes, and a couple of decades later, you observe NT. They have to match. And if they don't match, it's fantastic news. At least for theorists, it's great news. It's not single field inflation, it's something else. Something weird is going on. It's always the best case scenario, yeah? So this is very important because of that. This is called the consistency relation for tensor modes, yeah? Because it's a test on single field inflation. If single field inflation doesn't, if this doesn't happen, single inflation is ruled out immediately. There are other ways to rule out single field inflation. I will go through them in a moment with non-Gaussianity, but this is extremely important in my opinion, yeah? I think this is the most realistic test of inflation, if you ask me, yeah? Available. Why? Because I think there is a good case for saying that we might observe R sooner than later, but of course, that's wishful thinking. Tell me.
So if you do measure both of them, you verify that the consistency relation does not apply, that would be a robust evidence for inflation, but not that it happened with only a single.
It will be something else. Either it's not inflation, or it has to be something more sophisticated, multi-field inflation, or some single-field inflation with some new ingredients that were not written in the action that I wrote. So you have to write a different action, perhaps. Yeah, and they modified this relation, of course. So, yes. In principle, yes. People is not even thinking about NT nowadays. It's just too far. So what will happen as history progresses? If, okay, this is best case scenario, we observe R, right, next year, 2 more years, yeah? And now you know the value of R, and that predicts the value of NT. So now you start to improve your experiments, and you target that value for NT. You design it in the best possible way to go for that. I suppose I'm just, now I'm entering a territory which is, I don't dare to enter. But if it is not observed, that value of NT is observed something different, or it's just 0, whatever, it's okay, something is going on. Yeah? What's the question there? Okay, let me answer by drawing a plot which I was about to do now, if I understood correctly your question. This you will find everywhere, right? This plot of R versus NS or perhaps, will this be a right way to answer your question? Okay. And I won't put numbers. I'll just give you an idea, but to stress something I want to stress, is that you know that these bananas are somewhere down there in the plot. That means that R is pushing down the observation. You have to look at the plots and see the numbers, and NS is quite well constrained. I think that's a good job. And so just look at the plot, and perhaps that answers your question of how, the real value of R might be down there in a very inaccessible place. So, no, I don't know how close we are. Nobody knows, right? There is a value given by Starowinsky's model, which is fantastic because actually Starowinsky wrote the first paper on inflation. Yeah? I didn't tell you that in the first lecture. And that model continues to be there. It predicts a value. Yeah? It's amazing. It predicts there. Yeah? So it seems that Starowinsky's inflation is down there to be the model of inflation. Yeah? But of course, we don't know. This has to do, it's a matter of taste. Yeah? And it's very interesting because you can see, normally, those plots, you will see straight lines. And these straight lines, what they do, and I provided exercises to you in this direction, is to tell you where do different potentials exist. Yeah? And you can see that, for example, the potential that goes as phi squared is completely ruled out by observations. Yeah? So you cannot really satisfy current observations with the simplest potential possible, with a quadratic potential. Yeah? This was called chaotic inflation. And when I started working on inflation, this was the model to consider. This was a beautiful model because predicted it was a good candidate. Rule out. Yeah? And then observations continue to improve, and then this is ruled out, yeah? Phi. And now we enter into an arena where observations tells you that potentials cannot be, this is concave, right? They have to be, what's the name of the other? Convex. So that now they have to be convex, yeah? Or concave, it's convex, right? I'm trusting you. Yes. So V double dot has to be negative. Remember that epsilon is equal to V prime over V squared with factors, and eta was a combination of it was 6, right? I don't remember exactly. You have it somewhere, yeah? But okay, I won't focus on the factors. It's there in the notes. Plus V prime prime over V, if you examine the notes, yeah? So by restricting the spectral index, we can restrict the shape, and now by putting a constraint on R, which is basically epsilon, we have gained quite a lot of information about the potential, about the slope of the potential, yeah? So now we know that it has to be, not only have a slope, but has to be convex, yeah? So this region is a convex potential. Now we have and that's pretty interesting for theory.
This convex behavior has to, for example, for multi-field models, has to also be convex in...
Multi-field is a different story. The multi-field changes quite dramatically all of these parameters. So there's more space. So with multi-field, you can go back to this, yeah? But I don't want to poison your minds with multi-field. I have worked a lot on multi-field, so but I want to teach you the sort of the vanilla scenario, and then you move on from there to other places. But you take those decisions. Okay, I want to talk about the primordial non-Gaussianity soon, but let me just. Exactly. So remember that we have ns minus 1, which is this combination. Here it is. But this is depends on the slope, on the first derivative, and this has information about the second derivative. Yeah. And then R depends only on epsilon, which depends only on the first derivative. And so by constraining, just by constraining, we start gaining a lot of information about the shape. Yeah? So this is why you find in books, you don't find anymore this plot. Books were often written with this plot. Now books have, as I told you, this plot. Now you know why I wrote this plot. Because we need sort of this convex shape for the potential. Yeah? Okay. So there's been progress, after all. Yes? No, no. I made the difference between observing the amplitude and the tilt. And so the tilt is much more challenging. So my claim, which is not based on anything but except for having beers with observational cosmologists, is that measuring the amplitude is one thing, which is already hard, and measuring the tilt is way more harder, and that might have to wait decades after measuring the amplitude. Even? No, even the amplitude we don't know. Yeah. Yes. No. No, it's just when you apply for money, you cannot say that it's 3 decades away. You have to say it's now. We're going to measure it next year. You have to edit that out for the sake of everybody here. Okay, let me move to the next subject, non-Gaussianity. I'll try to be quick also with this. I was not quick with tensor modes, unfortunately. Well, as I argued in the overview of these lectures, there were very good arguments about that the primordial perturbations had to be Gaussian, and Roman has really substantiated that during his 5 previous lectures. But that didn't stop people asking the question, well, what about if it is non-Gaussian? How do we test that? Yeah? And remember, we're talking about the 70s, before inflation. Inflation was discovered in 79 by Starobinsky, and in the year 80 by Alan Guth, or also 79, I forgot now, almost simultaneously. And so what people did prior to inflation was to parameterize non-Gaussianity in a way that it could be tested. Yeah? And so this discussion is not the first time, and you have heard it in these lectures. One way to do it is to propose that the curvature perturbation indeed is Gaussian. So this represents a Gaussian fluctuation, which could be quantum, right? Could be, for example, the interaction picture field, which you know is a Gaussian field. We discussed that. Plus some deviation. Yeah. So the question is, what should we put here? And there is a low-hanging fruit here. The simplest thing that we could propose is something that goes as the Gaussian field, but squared. That's it. That's the proposal. Yeah? This is called the local ansatz. Yeah? It's just a proposal. It's not really based on any theory. Yeah? It's not that we know that a theory does predict that. 70s, right? There are some parameters chosen because the original proposal was not in this space, but this is what happens for the Gilbert perturbation. So 3/5 times a parameter, yeah, which parameterizes deviation from inflation, from Gaussianity, sorry, which is called FNL, yeah, and then we subtract the mean of the squared of the Gaussian field. Yeah, this is you can do it or you cannot, maybe you prefer not to do it, but it's just ensure that this condition holds. It's just comfortable to study fluctuations where the mean is 0. Yeah? And now you can ask what is the level of non-Gaussianity coming from here. And you know already that the 3-point function is a good measure of how much non-Gaussianity there is. And so this is a simple exercise. You can work out that R of x1, R x2, R x3 is going to be equal to 6 over 5 FNL times Rx1, Rx2, product of Rx1, Rx3, plus permutations. Okay, permutations of the coordinates. So you can see that there are pairings, and there are 2 more terms that you can write by performing those permutations. Yeah. Great, great. No, this is, we're in the year 70s. The inflation is not, it's not been proposed. We don't know whether R comes from a scalar field fluctuation. So this just reflects our ignorance. We just want to test non-Gaussianity, and we just come out with this answer. Yeah? What's the theory behind this? We don't know. Yeah? So this is just a proposal to test non-Gaussianity, nothing else. Yeah? It's just to, beware. We're talking about primordial non-Gaussianity as opposed to the non-Gaussianity that Roman discussed. Yeah? The universe is super non-Gaussian, but the initial conditions seem to be super Gaussian. Yeah? But nevertheless, we can suspect, well, maybe that's not true. Yeah? So let's try to test the level of non-Gaussianity. So this is a test. We write this proposal. No. So we're getting there. Yeah. So this type of 3-point function, if you moved into Fourier space, yes, sorry. Because we're discussing the initial conditions that Roman needs, right? So I'm trying to produce the predictions coming from the period before structure starts to form. Yeah? So that's where I'm trying to head. No, because because we are. This is the outcome of inflation, and inflation, well, it's a very different universe from what Roman was studying. So Roman was studying how matter fields, for example, coalesce by gravitational attraction. Yeah? Here we have nothing of that sort. Here the universe is exponentially expanding, and it's completely devoid of particles. There's nothing. There's only vacuum. Yeah. So that's the scenario we're studying, and we're trying to see whether there is some level of non-Gaussianity as an outcome of this period. We will do that. Yes. That's the hope. Yes. So I will give you the bispectrum that Roman takes as an input for the evolution of a structure. That's the idea. Yeah. But I haven't got there yet. I'm just telling you how people used to think about non-Gaussianity before we know how to compute it. Yeah? And you can show that in the bispectrum, which, by the way, I define it in a different way than Roman. Let me just clarify that in Fourier space, I use the convention where there is this product, this factor, 2 pi to the 3, a delta Dirac, yeah, plus the bispectrum. That's my convention. Roman, I think, was missing this, this factor. That's all. So it's a minor difference. And so the bispectrum that you get from this ansatz, let me write it for you, has the following form. Plus permutations. So this is the bispectrum that you get with the local ansatz, okay? And then it has become useful, I will do it here, to introduce a shape by the following rearrangement things. I will just clean up a little bit this expression and allow me to take the scale invariant version of the power spectrum, yeah? If we ever get to measure the non-Gaussianity, we don't really care about the running of the spectral index. The role of the spectral index is a small role, so let me forget about that, yeah? So with that, you can rewrite this in the following way. So this is just the amplitude. It's not doesn't depend on k, yeah? The k is just a constant. So I'm saying there is no k dependence, because I don't care about that detail. It's, you already know that it's almost scale independent. So you have that, you have FNL, and then you have the shape. And the shape function is found to be 1/3 K1 squared over K2, K3 plus permutations. Okay, this is what is called the local shape. Yeah, I'm just introducing some language because it comes from the local ansatz. Okay, but it has become useful, and remember, this is just a test of non-Gaussianity, and now that we're doing a test in Fourier space, has become useful to introduce other shapes for no better reason than just to try to constrain them, yeah? We're still before the invention of inflation, yeah? I'm mixing the history. This happened after the invention of inflation, but people introduced other shapes, so you can actually write this as the sum of the type of non-Gaussianity, which is parameterized by FNL. So now we say FNL local, or FNL equilateral, or FNL orthogonal. There are different types of FNL, and the type of the shape, yeah? So the local shape is this one, so I should now put here local. Yeah, now you know the local shape, and I will not write for you the equilateral shape, I will not write for you the orthogonal shape. Just go and look at them out in the notes, for example, yeah? They're just functions of K which are different from this one, yeah? Please.
Just to be sure, is that only a proposal?
It's only a proposal. Yeah, no inflation yet. Okay? It's just to make the story of inflation more entertaining, because there are a bit of confusion sometimes when people try to understand the predictions of inflation in terms of these very common tools, which are the shapes. So let me, I wanted to go through this first before telling you what inflation does. Any questions, please? Yes? Excuse me? This one? Yeah. So this is just a proposal of how to search for non-Gaussianity. It's just a convention. It's an ugly convention, I agree. It's because this was defined in the context of large-scale structure. So this is a better-looking expression in a different context. Yeah, but when we do it in the sense of the context of the primordial curvature derivation, it acquires this factor, which is just slightly different. It's nothing. It's pure convention. it's not really useful, that 3/5 for the present discussion. Good. So some current constraints, I'll give you the local at least, and the other ones are worse and worse. This comes from Planck to, this is 1 sigma, and then equilaterals, these are just constraints. So look at how bad it is. They're all bad, right? And it's good to know that, so this is orthogonal, and this is 34 plus minus 33. You should go and read the papers by Planck. They're really good papers. WMAP papers are fantastic. You should read them, yeah? Yes. So first we arrive to the expression that is predicted by the local ansatz, yeah? Yeah, and I was not very clear here. Then I said, well, because of that, people invented other shapes different from this one, yeah? And so now one writes the bispectrum as a sum of different contribution, not only the local one, which comes from there, but other shapes which have been invented, yeah? And one is called the equilateral, the other is called orthogonal. And to be fair, I should write them down for you to see them, but you will not learn anything by seeing them. You need to have a lot of experience visualizing them, yeah? It's better to see plots, yeah? So at least you know the local one, which is easy to write, yeah? But this is just a creation. People have created these shapes to constrain them, yeah? Okay, so now the question is, well, what has anything of this to do with inflation? Maybe nothing, yeah? Over there? NL, this one, it's just a name. FNL is a nonlinear parameter, yes? Where there is an LL? It's just a brain disorder I have. Yes? No, these are templates, let's say, to search for primordial non-Gaussianity on the initial conditions, yeah? So Roman actually studied the evolution of non-Gaussianity, how non-Gaussianity forms via gravitational interaction, yeah? In fact, he needs, for him, this is almost irrelevant. For him, this could be 0. This could simply not exist, yeah? Yes, exactly. You can do the same game here, yes? You can plot them in the same way, so people still visualize them in the same way. So this is a function of 3 scales, yeah, 3 Ks, yeah? No. In terms of thinking about them, they're the same things, yeah? You can look at them in the same way. So you can, for example, study the squeeze limit, yeah? And in the squeeze limit, actually, the local shape fires up, it diverges, yeah? Because if you take one of the Ks too small, you see a divergence, yeah? That's it, okay? The other shapes behave well, yeah? The equilateral one doesn't fire up, and the orthogonal one doesn't fire up. So this is behind the reason why this is better constrained so far. It's because it's easier to extract from data, so on and so forth. Yeah. Good. Let me get to inflation now. I think I'll manage in 20 minutes to connect inflation with all of this previous story. How do we compute the bispectrum in inflation? Well, not this way. I mean, this is a parameterization. It has nothing to do with theory. It's just a proposal to search observationally non-Gaussianity. But we developed the tools to compute non-Gaussianity for quantum fields. Do you remember that? We have an equation there waiting. I told you, please hold on to this equation. Yeah? So I'll write it back. in Fourier space this time. I wrote it down in coordinate space, but now I'll move to Fourier space. Yeah, and the equation looked like this. Now we're talking about the quantum R. Yeah, in that occasion we talk about the quantum phi, some scalar field. Yeah, same story. And so this will be K1. It still depends on tau. This is the Fourier transform of the field operator. So we have that K2 tau. Yeah, at the end, at some time when all the modes are super horizon. Okay, there we have. And this was equal to what? Well, to the same expression, but with the interaction picture field, remember? So here we have Ri, Ri, Ri. But you know the value of this, right? This is 0, because these are Gaussian fields. Yeah, these are fields that obey linear equations of motions, that, and they're just Gaussian. Yeah? So this is 0. That was our result at that time. Yeah? We wrote it in full generality. Go back to the, not right now, just keep listening to me, but then you go and check that equation. Yeah? And then comes the next contribution, which comes from expanding this Dyson formula, remember? And this expression was the following. Now, all of this is to the context of what we're doing now, which is during inflation with conformal time, so that's why you see conformal time there, which goes from minus infinity to some time below 0, d tau prime, and now we have the vacuum, and now we have a commutator between the interaction picture field characterizing inflation. So there we have. We have a second one, and we have the third one, and now we have to put here, as usual, I'm running out of a blackboard, and now we have here the Hamiltonian. The cubic Hamiltonian, remember, we have to put the interaction Hamiltonian, so here we will put the cubic one, yeah? There is the fourth one, there is there are many orders, but the lowest order is the cubic one that describes nonlinearity. So let's put the cubic one, yeah? And it's also in the interaction picture. I close this, and then this is 0. By the way, this is evaluated in tau prime. Sorry, I just ran out of blackboard. But this Hamiltonian, remember, depends on time, and it depends on tau prime, which is being integrated, okay? So this quantity here lives at all times. The Hamiltonian see all the time history, but here we have the fluctuations evaluated at the final time that we want to compute the endpoint correlation function. In this case, the 3-point correlation function. Well, yes, this was from some initial time. Yeah, if you go back to the second lecture, you will see that we put here tau naught. Yeah, but now we want to remember that we put the vacuum in the far past at minus infinity. We say the universe starts completely devoid of particles. It starts in the vacuum. So we put minus infinity. Yeah. In actual computations, it doesn't matter because you reach minus infinity very quickly for these modes. The universe is expanding so fast that you reach the state of the vacuum very quickly before horizon crossing. Yeah? So it's just a technical detail. It doesn't really matter. Good. Next step. So I'm just sketching the steps that you need to perform to compute the bispectrum. And I was not planning to compute it at all, but you can see the computation in the notes. We need the Hamiltonian to cubic order in the fluctuations. Where are we going to have a hold on that Hamiltonian? Where do we take it from? Yeah? Well, we have the action. Remember this monstrous expression I wrote yesterday of the action to all orders. Yeah? So you go back to that expression that I didn't even dare to write completely. I just stopped halfway. But it's here. It's a huge expression, right? And from there, you compute the cubic part of that action is really it's difficult. Huh? So this one I'll be fair. It's so difficult that people fail once and once again doing this. Yeah. And there were many papers at the time proposing, and somebody else discovered a mistake, and then everything restarted. And this took quite a long time, until 2002, when Juan Maldacena wrote a paper on non-Gaussianity. And to my knowledge, that's the first correct computation of the bispectrum in single-field slow-roll inflation, yeah? Without mistakes. So I'm sort of showing what was done in that paper. And basically, yeah, I don't have too much time, but it's fine, it's fine. So I'll give you a sense of what the cubic action looks like. After a field redefinition that I will comment on soon, the action looks like this. This was after a lot of hard work. I mean, now it's easy to know what to do because the hard work is done. And so one can really learn this. It's not a problem. But it was hard. So that's the second term, and then there is a third term. And you can see Rn instead of R alone. Yeah, and that's the cubic action. And this comes, give me a second, after field redefinition, which takes place, but I don't think it's worth giving you the field redefinition. Let's just keep track of the ideas here. So the important thing is that this is the action describing the cubic interactions. And that's the place where we have to extract the Hamiltonian. You had a question? Right. It was just hard because, well, one of the aspects that I'm aware that there was an obstruction is that most of the versions of the actions that people got by handling them, they were not of order epsilon squared. They were of order epsilon. Yeah. So one of the difficult things that Maldacena did was to handle the action and perform a lot of partial integrations until getting an expression which is quadratic in epsilon in the slow-roll variables. Yeah, and this is the correct expression. Why? Because it's subleading compared to the second-order action. So it has the right structure in terms of slow-roll parameters. Yeah. So from an action which is linear in epsilon, you were going to have a huge signal, which was not there. Yeah. But it was just, that was one part of the story, not the only one. Yeah. Yeah, and people knew that. Yeah, that could not be because how it can be that the next term in the expansion is actually is not only of I mean it's difficult to compare, but it's going to be huge compared to the first one. Those kind of details were present.
So where do you use the potential gets in this expression?
Through these lower parameters. Yes. That's you always go for that. Go for these low parameters, not the potential slow parameters. It's better to keep track of the expansion, not the shape. Yeah, and that's why working with the curative provision is simpler in that sense. Yeah, it's a favorite choice nowadays. Okay, so yeah, I think I'm almost done actually, because I am skipping many details that will only unmotivate you. So I'm just sketching the steps, yeah? And now you have 3 contributions for the Hamiltonian. So for example, you can have one Hamiltonian which comes from this term, for example. Yeah. This is written in cosmic time. We need to go to co-moving time, right? Conformal time, sorry. So that can be done, no mysteries, basically same steps that we've done before, and you end up finding something of this form. Is proportional to epsilon cube, and then an integral in Rn prime squared, and then you can compute another one and another one, which just come from the next operators, right? So it's basically it's the same thing. It's just Rn nabla Rn squared, and the third one is direct. It comes from there. I give you as an exercise, but it's really unnecessary. And now, I just want you to have a sense of the steps, right? Now you pick each one independently if you want, and you plug them here, yeah? And you will see that now you have to make a commutation between something which has 3 fields in this side, and here there will be how many fields? Also 3, yeah? And in the interaction picture, this I means, what it means, I means just replacing here all of these fields by an I, yeah? Okay? And now you have to perform weak contractions between creation and annihilation operators, yeah? Computation is not really hard. It's boring, perhaps, but it's not hard. You have to perform contractions between 6 fields inside the vacuum. So this is the kind of operations you need to do, right? So for example, A daga, A daga, A daga. Just to give you an example of one type of contraction you need to perform. There are many more. There are all the combinations, yeah? And there are smart ways to do it, so you can... And so after that, you have to integrate in time, yeah? It's not a big deal. It's, they're basically the Hankel function. When you neglect the spectral index, it becomes a very simple function, yeah? When nu is equal to 3/2 and nothing else. And so the integrals actually can be performed. It's fantastic. And so I'll tell you the result of what Maldacena got. Exactly. Comes from there. I mentioned it's not easy. So there's a lot of steps up until that point. Yeah, and that's not a complete action. I erased even higher order terms in the slower parameters that we don't really need in this discussion. And so, after much hard work, nowadays there are more efficient techniques actually based on Feynman diagrams to get to the same result. You get them almost instantly, but this is the way it was done originally. Okay, and so here we have so that's one term, and then there is a second term, and that's it. It's not too awful. I'll tell you in a moment what is big K. Okay, and I close, and big K is equal to K1 plus K2 plus K3. That's it. This is the famous result in that 2002 paper by Juan Maldacena. A very influential paper in learning how to compute the bispectrum. This was a big step in the... And now, well, what do we do with this? This is the prediction from inflation, right? Single field slower inflation. You can see that is proportional to epsilon, yeah, the amplitude of the power spectrum is, sorry, of the bispectrum is suppressed by its lower parameters. That's the first outcome. You can, of course, rewrite this. You just play with this, and you write it in a way that is basically proportional to FNL, some number, whatever, delta square of K1, how was this? Was like this, right? Times a shape, for example, yeah? Okay, you know what I mean? There were more factors, but I want to concentrate on them. And you just compare, yeah? Compare the two sides. You can do that, I'll leave it to you. And you will learn that FNL is basically goes as epsilon, combinations of epsilon and eta, yeah? So the prediction from inflation is way far from those observational numbers I show you, yeah? Okay, that's a first outcome. I mean, what shape is this? You might ask, well, is this equilateral, local, orthogonal? Well, it's mostly a combination between equilateral and local, yeah? You have to, you didn't see what is the equilateral, but you have to trust me. So you can disentangle this into two shapes, and one will be equilateral and the other local. And people studied what is called the squeeze limit, which has been mentioned, right? You heard about the squeeze limit of the bispectrum, yeah? And so in that paper, there is the limit of one of the momenta being much smaller than the other two. Let's say K3 much smaller than the other two. And you can check the following result, that in that limit, this expression collapses to something quite amazing, collapses to minus 2 pi to the 4 over 4 I need to check this factor, by the way, but for now it's not it agrees with one of the paper I used to design the notes. You get to this. This is called Maldaceno's consistency relation, yeah? It's a statement about the squeeze limit. It's the squeeze limit, when one of the moments is much smaller than the others, the bispectrum becomes proportional to ns minus 1, yeah? This is not an accident. There is a reason to understand that. I will not cover it here, yeah? But this is a result. And it so happened that if we go back to the initial discussion on non-Gaussianity, about the local non-Gaussianity, remember the local shape and all that? Well, the local shape has basically the same limit, yeah? Same limit where you can compare this with FNL local, yeah? So now I can finally connect the two stories, right? The parameterization through local FNLs, through the local ansat, and this prediction, yeah? So basically, there is a prediction coming from single field lower inflation, which is that FNL is some factor, I don't remember which one, minus ns minus 1. Okay? And so it's important. By searching local non-Gaussianity, you might find this result. This is a prediction for inflation. Okay? Now, let me cool down a little bit expectations. It so happens, and this was shown more recently by Tanaka and Urakawa, and later on by Matias Aldarreaga and Enrico Payer, almost simultaneously, that in fact, the observable value of FNL needs to account for a correction. Yeah? This is, I cannot explain it right now, but this has to do with taking into account the fact that observers are following geodesics, right, in a perturbed universe. Yeah? So let me just give you a sense. The longest wavelengths are modifying the movement, let's say, of a local observer, of us. Yeah? We're being subject to sort of we need to take into account that correction, let's say. If you take into account that correction, let's correct it, taking into account that correction, the fact that we follow geodesics. The correction is ns minus 1. And so they vanish. So the real prediction coming from single field inflation is that the squeeze limit is 0, and therefore FNL local is 0. There is no FNL local. There's no local shape here hidden. Yeah? That might look like a blow. Yeah? I consider it the best news possible. Yeah? Because it means something spectacular. It's as spectacular as the previous statement about that there is a consistent relation in the case of tensor modes. Yeah? This is telling you that if you measure some level of local non-Gaussianity, that's it. We rule out inflation, single field inflation. Yeah? Multi-field inflation can avoid that, and multi-field inflation can predict deviations from this. Yeah? So if you measure local FNL, it might be a good indication that other types of inflations are in place. But we know very well that this holds for almost every single field inflation model, even not the vanilla model of inflation, but even more general models of inflation. So this is quite a result valid for the observable FNL local. Yeah? This is a combination of the prediction plus a correction of the. Well, okay, I think you're thinking about ultra slow roll. Right. There's been a debate there too, but no, but I agree with you. I agree with you. Yes. Yeah. So let's talk about that later. No, but no. But I want to be fair. You're completely right. Let's be precise. This will be single field slow roll scenarios, but you can have, for example, speed of sounds changing the story and so on and so forth. So effective field theory of inflation and all that. Okay. Now basically I said all of what I want to say, and yeah, I think that's an awesome result. Quite surprising, and not completely absorbed yet by the community, but I think it's correct. Yeah. Okay. Thanks a lot.
One here and one there.
Thanks, Professor. So, okay, according to this expression for the bispectrum, I mean, single field slow roll inflation predicts a small but non-zero value of non-Gaussianity, right?
Okay, good. Because thanks for the question, because it might give you the impression that when I discussed this part of the blackboard, I was implying that the full signal is 0. No.
Okay.
Here I'm talking about the squeeze limit. Yeah. The squeeze limit sort of allows you to identify the local part because you can do the match. Yeah. Sure. So now this is telling you that there is a local component which disappears, and what is left doesn't blow up in the squeeze limit, and it's something which has more of what is called an equilateral shape. Yeah? Okay.
No, but my question is actually, so is that a consequence or an effect of the curved space-time during inflation? Because, I mean, the perturbations from the inflaton field or the co-moving curvature perturbation, they are quantized based on a free scalar field, right? We should, in principle, be Gaussian, but in inflation, you're in a curved space, so does that induce non-Gaussianities?
Yes, I mean, let's say the way I will phrase it is that during inflation, the Hubble parameter is changing very slowly, yeah? So the universe doesn't look exactly the same at every rate. It's almost the same, but if you compare, for example, the universe at one time and then later on at several e-folds later, you will see, okay, the Hubble rate is different, yeah? And those are parameterized by epsilon and eta. And epsilon and eta sort of couple the modes through the interactions, yeah? That's why the cubic terms, which couple the modes non-linearly, produce these interactions. And in the end, those interactions translates into what we are calling non-Gaussianity, yeah? So this breaks the scale invariance, but in principle, you could still have something which is not scale invariant and Gaussian, yeah? But the dynamics of inflation sort of tie them together, yeah? So in the end, non-Gaussianity is tied to the fact that the scale is changing in time through the interactions of the modes, yeah? That's
A very quick follow-up. So if it was exactly de Sitter, we would not have non-Gaussians, even though this space-time is curved.
Right, right, exactly. But then remember that in exactly the Sitter is just a permanent state where but this is important because if let's say inflation is exactly de Sitter, well, there should be a mechanism that allows us to escape, yeah, and that mechanism, whatever it is, could produce non-Gaussianities nevertheless. So
Thank you very much.
In that extreme case, yeah.
First, thanks for the course. Really enjoyed it. In this setting, we considered leading corrections to the linear theory to generate non-Gaussianities. Would I be able to generate non-Gaussianities if I choose another initial state instead of the vacuum state, like a thermal state, for instance?
Absolutely. So when we've done these computations, we take the state of the system as one which was the vacuum in the long time ago in the past of inflation. Remember, I mentioned that you have to be careful about stating things about the vacuum, yeah? Because in the Heisenberg picture, you just decide, okay, this is the state, yeah? But through evolution, this state could later on look as filled with particles, yeah? So our attitude here was to decide that the state of the system, which is time independent, remember, the state of the system is time independent in the Heisenberg system, in the Heisenberg picture. The state of the universe right now is exactly the same as the state of the universe prior to inflation. It's time. What has changed are the operators which evolve in time in the Heisenberg picture, right? That's and so long a time ago, when inflation set off, right, we choose that state to be the vacuum. So we say initially the universe is completely empty, yeah. And now you let inflation go, and it start producing these vacuum fluctuations, yeah. At the smallest scales, it will always look like a vacuum, yeah, because very small scales is like going back in time in the case of inflation, yeah. Now, if you change the state for something else, you are almost for sure going to produce non-Gaussianity, yeah, because now the state itself has particles which you have to define how are they distributed, yeah. And that, well, almost by default, will force you to decide what is the statistic of that, and it could be non-Gaussian if you want. So just the mere fact that you construct a state, other than the vacuum, for sure will imply non-Gaussianity. Yeah.
Okay, so in the end, the prediction of inflation that the primordial spectrum was Gaussian depends on both choosing a vacuum state and linear ordering perturbations.
And that we're close to linear, yes,
okay,
yes. So,
okay.
So, of course, as all in life, there's always assumptions. I have not escaped that burden. In my opinion, these are minimal assumptions, but nevertheless assumptions. So we're assuming that at very small scales, during inflation, the universe looks empty. Yeah, there's nothing to be found there. Yeah, and then the wavelengths grow, and then the universe starts to get full of particles at longer wavelengths, and that's called gravitational production of particles. And this outcome is for these models, right? You can now change the model. You can propose a different action that I wrote. That will not be single field slower inflation anymore. Could be single field, but something else. And then, for example, there are beautiful papers on what is called effective field theory of inflation. Yeah, and those enhance the magnitude of non-Gaussianity. Yeah, if you introduce what is called the sound speed, and there is an exercise about the sound speed in the notes, which, well, we have talked about the sound speed, right? I wrote it in a few places already. Then this signal basically gets improved. I have to choose somewhere where to write. The whole thing gets improved by a factor of 1 minus 1 over c squared, yeah, without an epsilon. Yeah, and so this is this is a possible way of amplifying the signal. And whenever you read proposals for new experiments targeting non-Gaussianity, they will never refer to single field slow inflation because it's too far, but most likely to effective field theories of inflation. Yeah, that's the way to justify funding in this field.
Okay. Any further questions? So I don't see any hands. So let's thank Gonzalo again for this
No,
very nice set of lectures. So just to remind you that we have a Q&A session at